So let's begin and I'd like to talk to you today.
Hello, my name is Daniel Lewis. I'm a professor of material science and engineering here at RPI, and today I'm going to talk to you about electron microscopy. There are three important techniques that I'll discuss today. The first allows us to understand the morphology or the shape of a material, and for that we use secondary electrons. The second helps us to understand the crystal structure of a material, and for that we use backscatter and diffracted electrons. And the third helps us to understand the chemistry of materials, and for that we use X-ray photons generated from within the sample itself. Before I get into that though, I'd like to describe how we generate electrons, and then how we shape the electron beam to interact with the sample. To generate electrons, we use something that's similar to an incandescent light bulb. We take a tungsten filament and run a high current through it, and then the electrons start to boil off of the surface. And through some electronic circuitry attached to the gun, the so-called gun of the electron microscope, we focus that electron beam and inject it into the electron column. Those electrons travel through electron lenses, which are made from an iron core and copper windings. The strength of those lenses depends on the amount of current that's flowing through those copper windings. The more current, the stronger the lens. To shape the beam, we stack the lenses into what's called an electron column, and from there we can shape the beam, and we could even scan the beam across the surface of the specimen. And this scanning operation is what makes the scanning electron microscope such a great tool, because we can correlate structure and morphology and chemistry across a spatial area on the surface of the sample, and you'll see that in some of the images that I'm going to show you. There are two types of interactions that occur between the electron beam and the specimen, each giving us different types of information. The first type of interaction is called an elastic interaction, where the electrons are diffracted or scattered through very large angles, and those electrons contain structural information. The other type of interaction is called an inelastic interaction, and from there, the electrons can generate things like secondary electrons and X-rays. It's important to consider how the signal gets to the detector. And for that, we have to consider some important characteristics. For example, how deep into the sample was the signal generated? How far from the primary point of entry did the signal emerge? And what distance did the signal travel through the specimen before it emerged? When we consider these three things, we can better interpret the information that's present in the signal. This graph shows the types of signals that are generated in the electron microscope, and here I've circled secondary electrons. That's the first one I'd like to talk to you about. To detect secondary electrons, we use a so-called Everhart-Thornley detector. This detector sweeps up those secondary electrons and then uses what's called a photomultiplier, which changes that electron signal into photons, and then those photons are focused, kind of like a fiber optic cable, into a photomultiplier tube, where they're changed back into electrons and then amplified. And so these secondary electrons are very low energy, and they're emitted from very near the surface of the sample. This makes them highly responsive to the topography of the sample, and also highly responsive to the primary energy of the beam. This image is of a metal powder and is a false color image that's composed of red, green, and blue. And by mixing that red, green, and blue imaging, we can get information about the surface topography of the sample and the surface roughness of the sample. This image was collected by Andrew Zonenberg, who was a student in my Introduction to Electron Microscopy class. He created this image from 3 different beam energies, colored them, and recombined them so we could learn something about this metal powder. The second kind of signal that I'd like to talk about is a backscattered electron signal. These electrons are Bragg diffracted from the surface of the specimen, and what that means is that these elastic electrons emerge at particular angles from the surface of the specimen. And at these very special angles, the electron waves reinforce or amplify each other. We can then collect those amplified backscattered, diffracted waves to produce a pattern like the one on the upper right-hand corner. This is called a Kikuchi pattern. And those bands that are present on this image tell us about the crystallographic orientation near the surface of the specimen. So we know how the atoms line up near the surface, and therefore we know how the crystals are oriented, and from that we can say something about the mechanical properties of a material. In this example image, this is a zinc alloy, and this zinc alloy has got many different crystals present near the surface of the specimen. The different colors represent different crystallographic orientations, and it allows us to say something about how this material was formed. In this particular research, we're trying to study the formation conditions of the Earth's core. The last signal I'd like to discuss are characteristic X-rays, which are generated from the surface of the sample. These X-rays are created by an inelastic interaction where the incident electron beam ejects an inner shell electron. That leaves the atom in an excited state. The outer shell electrons then trickle down to fill those inner shells, and when they do so, they emit photons. Now the good news is we can collect these photons and measure their energy, and we do so in a silicon detector. When the photon enters the silicon detector, it creates electron hole pairs in the silicon, and then we sweep up those electrons and then count the charge. And the charge that's produced is proportional to the energy of the X-ray. Now, if we do this over all energies and count up the number of photons, we can produce a picture like this one that shows characteristic peaks. Part of my research program involves looking at lead-free solder alloys that contain silver and tin. And here you can see a peak that we have labeled silver and peaks that we've labeled tin and a small peak that's labeled gold. Using this information, I can tell how the elements partition or spread themselves out across the material. Here's one such image that shows the elemental distribution of copper and silver in a lead-free solder alloy. And from this picture, I can tell where the copper is and where the silver is and how they combine to give the solder its special properties. In summary, we've discussed three important techniques in the electron microscope. As a metallurgist, I rely on these three techniques to give me information about the materials I'm interested in. In metal powders, I use secondary electrons to tell me about the topography and morphology of specimens. In my research on the Earth's core, I use backscatter electron diffraction to tell me about the crystal structure and the texture of these materials. And in my research on lead-free solder alloys, I use energy dispersive X-ray spectroscopy to tell me about the chemical makeup of these lead-free alloys. Thank you for watching.